All right, let's get right into it. Today, we're going to tackle one of the biggest, maybe the biggest challenge in the quantum world. How in the world do you build qubits that you can actually trust? It's a fascinating story, a real journey from mind-bending fragility to some truly ingenious resilience.
Just picture that for a second. The sheer, ridiculous impossibility of it. You know, that intense focus, the constant wobbling, knowing that just one tiny slip, one wrong move, and the whole thing comes crashing down. That feeling of exquisite, high-stakes instability, well, it's the perfect way to get your head around.
That insane high-wire act, that's pretty much the day-to-day existence of a single quantum bit. It holds this incredible, world-changing promise, but it's always just one tiny disturbance away from completely tumbling into chaos.
And this, right here, brings us to the central paradox of all of this. See, in quantum computing, a qubit's greatest strengths, its superpowers, are also the source of its greatest weakness. You could say it's the ultimate price of power.
So, let's meet the main villain of our story, decoherence. And here's the thing. It isn't a bug in the system, it's not some mistake we can patch. It's just inevitable. The universe is a noisy place, you know? And any little stray bit of heat, a tiny magnetic fluctuation, even a passing cosmic ray, can whisper to our qubits. And that's all it takes for its delicate quantum state to just poof. Collapse. The magic trick is over before it even has a chance to get good.
And that really highlights the fundamental night-and-day difference here. Classical computers are built on rock-solid stability. We expect a bit to be exactly what we left it trillions upon trillions of times. But quantum computing, it has to embrace this built-in fragility. That soap bubble state is precisely where all its incredible power comes from.
Oh, and just to make things even more difficult, the universe has this really strict no-cheating policy. It's called the no-cloning principle. Basically, you can't just copy a qubit's quantum state to make a backup. So if that information gets corrupted or lost, it is gone, for good. There's no Control+Z, you just can't hit undo. So, that's the grand challenge, isn't it? We've got this immensely powerful, but incredibly fragile instrument that we can't back up. So if we actually want our quantum computer to do something useful, to play an entire symphony instead of just one fleeting wobbly note, what do we do? How do we protect it?
Well, the answer, and really the hero of this entire explainer, is this brilliant strategy called quantum error correction. We just call it QEC. It's a ridiculously clever way to find and fix errors without actually looking at the qubits and destroying the very quantumness we're trying to protect.
I absolutely love this metaphor. Instead of relying on one single, fragile qubit, you braid the information across many of them. Think about it. If one physical strand in a braid gets frayed or snaps, the overall braid, the logical information, it stays strong. It remains intact. It's this beautiful, powerful concept of strength in numbers.
So how does this whole braiding thing actually work in practice? Well, let's start with the simplest possible version, a kind of basic protective spell known as the 3-qubit code.
Okay, so let's walk through this. It's pretty cool. First, we encode our single piece of information, let's say it's a quantum 0, across a team of 3 physical qubits. So 0 becomes 0, 0, 0. Now, let's imagine an error. That cosmic whisper comes in and flips the middle one. So now we have 0, 1, 0. Here's the magic part. We don't look at the qubits directly. That would collapse the whole thing. Instead, we use helper qubits to just check the relationship between them. We ask, hey, are qubit 1 and 2 the same? The check comes back, nope. Then we ask, what about 2 and 3? Nope, they don't match either. And aha, the only way both of those checks can fail is if the middle qubit is the rogue one. So then we can apply a gate to just flip that one back, restoring our original 0, 0, 0 state, all without ever having looked at the information itself.
Now that 3-qubit trick is fantastic for getting the basic idea, but a real quantum computer, well, it's a massive orchestra. So to guard an entire symphony, we need a truly professional-grade strategy. And that is where something called surface codes come into play.
I want you to picture a living chessboard. Some of the squares on this board are the data qubits,
They're the ones actually playing the melody of our computation. But scattered all among them are ancilla qubits, or guardian qubits. Their only job, their entire purpose, is to constantly check on their neighbors and report back if anything looks out of tune. This creates a resilient, self-correcting fabric.
And here's another great way to think about it. The logical information, the thing we actually care about, is like a frail, priceless crystal statue. It's precious, it's fragile. The hundreds or thousands of physical qubits that surround it, they're like foam bricks packing the box. Their job is to absorb all the bumps and shocks from the outside world, sacrificing themselves so that the statue inside remains absolutely pristine.
And this brings us to the just staggering reality of what this takes. The overhead is immense. To create just one stable, reliable, error-corrected VIP logical qubit, you need somewhere around 1,000 physical qubits to act as its bodyguards. That is the mind-boggling scale of the engineering challenge that researchers are tackling right now.
So, okay, let's pull all of this together. We've gone on quite a journey here, right? From a single, wobbly qubit on a tightrope, all the way to a robust, protected, logical qubit that's actually capable of performing a real computation. From chaos to creation.
So let's just quickly recap the story. We started with our villain, decoherence, that silent, ever-present thief of quantum information. Then we found our shield, quantum error correction, that incredible strategy to encode, detect, and correct errors on the fly. We learned that a logical qubit isn't a solo act. It's a massive team effort, woven together from maybe thousands of physical qubits. And finally, we saw that the architectural blueprint for making this all work at scale, the surface code, is what's paving the road to a truly reliable quantum future.
And we'll end on this thought, because it really gets to the heart of why this work is so profound. Every single tiny error that gets caught, every quiet little correction that's made, is a monumental victory. It is the painstaking, brilliant work that turns the fragile, chaotic potential of the quantum realm into an unbelievably powerful tool for creation.